Well, I think it's time to draw some connections between a few equations that we have seen. They've been separate so far, but let's put them together. Equations, or more likely concepts or notions. The notions of an equilibrium constant, the notion of a free energy, of a change in free energy in a system, or in this chapter, the notion of a cell potential, like the likeliness of a battery to be a good battery. In previous chapters, we've talked about equilibrium constants. We said that if the constant's bigger than 1, the reaction tends to go forward, or the forward reaction is favored. We've also said that the free energy change, if the reaction is spontaneous in the forward direction, it would like to be negative. Talked about that in the thermodynamics chapter, which was some time after the equilibrium unit. Now, let's use that and a new equation for the free energy in relationship to the cell potential, although you might not have seen this one before. So if my cell potential is positive, that means it's tending to be a good battery, or I could make some kind of transfer of electron happen. No, I could see a transfer of electrons happening in a spontaneous way. It sort of wants to go forward and transfer electrons. That's a positive E cell. Although this equation has a negative in front of it, that implies that if this is positive and this is positive and this is positive, my overall will be negative, and that's reflective of a negative free energy change, and that's reflective of a spontaneous reaction. So assuming you haven't seen this equation before, it's pretty handy and pretty simple. The standard cell potential, as we've calculated now for some time, several classes and videos and discussions, equal to the number of electrons transferred times a constant. The constant is called Faraday's constant. Number of electrons transferred just has to be, determined on a case-by-case basis. How many electrons are you talking about? So FYI, and by the way, you'll be given Faraday's constant, but it's kind of interesting and curious to see where it comes from and how it's arrived at. You get a value. One electron, it's determined from physics, and particle physics has a charge of a small number of coulombs. But if you take 1 full mole of electrons, that's a large number of electrons. So Avogadro's number times the charge on 1 electron gives you, voila, this funky constant called Faraday's constant. The units are coulombs per mole of electrons, or another way to say it is joules per volts, moles of electron. Or in other words, it's 1 coulomb is equal to an energy unit per volt unit. If you've ever had a course in physics, second semester physics or electronics, I'm sure you've heard of a volt. Wait a minute, you've heard of a 9-volt battery, a 12-volt battery. You know what volts are, sort of. You've heard of them. But us in chemistry, we don't deal with it too much, do we? But of course, we've been calculating standard reduction potentials in volts, and so, yeah, it's been around. Let's practice that a little bit. Oh, no, wait, let's try another equation. So if I put those previous two equations together, I get another equation, that relating the free energy in one electron transfer and the free energy to an equilibrium constant. So I suppose I could consider every equilibrium to be potentially a redox. Maybe it is, maybe it isn't. But if it is, and I have a standard cell potential, I can get an equilibrium constant for that. And that's done by relating the free energy change in one equation and another equation. Natural logarithm of the equilibrium constant equals the number of electrons transferred times Faraday's constant times the standard cell potential divided by R, the gas constant. And the Kelvin temperature. Let's just take a look at how that works. Oh, so if I were transferring 2 electrons, by the way, 2 electrons times Faraday's constant times the cell potential. So I'd either have to know the cell potential or be given the half reactions to be able to figure that out. Oh, here they are. So it looks like the cell potential, although I don't like to write it this way. I like to turn this one backwards as a reduction. Oh wait, that's a reduction. What? let's see. Oh gosh, that's why I hate writing it like this. So that's ridiculous. All right, so take my word for it. The cell potential is 0.463 positive, and if that's true, the positive here and the positive Faraday's constant and the positive 2 moles of electrons transferred gives me a positive number, but there's a negative in front of the equation, so the standard free energy change is negative, implying that the reaction kind of wants to go forward. So saying this is positive and this is negative are different ways of saying the same thing. I could also say, what's the equilibrium constant for that? So I could guess what it is. If this is positive, it wants to go forward. If this is negative, it wants to go forward. What will K of equilibrium be if it wants to go forward? The answer is bigger than 1. Question, how much bigger than 1? Well, that's a good question. Here, the gas constant has to be in energy units of joules per mole Kelvin to make the joules of the free energy match with the joules here. And here it is. So if I had the free energy as, would that be 89,400-ish joules per mole, the gas constant, that's a negative, and this is a negative from the equation, times the gas constant times the Kelvin temperature in the denominator. Solve for, so if I get an answer for this is 36.1, to get rid of the natural logarithm, I take e to the 36.1 and e to the ln of k. The e to the ln cancels, and yeah, voila, I have, it's a big number. Whoa, 5 times 10 to the 15th. That says it really wants to go forward. Did they, in the equation, draw it as an equilibrium? They didn't. But it's legitimate to say, well, if it goes forward, it might come backwards a little bit. But if my equilibrium constant is 10 to the 15th, that means it really, really, really wants to go forward. And very rarely would you see anything very much going in the reverse. Excuse me, here's another equation, reaction. And you see the answer, rats. All right, well, we'll get over it. So if I look at the oxidation state of oxygen is 0 here. The oxidation state of this oxygen is -2, and there's 2 of them. So 2 -2's go to 2 zeros, and so that's actually a transfer of 4 electrons. So n equals 4 here, and the Faraday's constant and the cell potential, -2.06. So you just take -2.06, Faraday's constant, and the number of electrons transferred. There's a negative here and the negative here, and it comes out to a positive free energy change of 795 kilojoules positive, saying if this is a negative cell potential, is it likely to, I could make a battery to go forward in this direction? I could harness and transfer electrons from here to this situation to this situation. No, it's not very likely. It's not going to happen. It's not going to want to happen by itself. Likewise, I could guess that the equilibrium constant would be super duper small because the cell potential is negative and the free energy change is predicted to be positive, calculated to be positive. So I relate the free energy change to the RT and the ln of the equilibrium constant, solve for the equilibrium constant. Oh my goodness, it comes out to 10 to the negative 140th, which is so insanely small that it's not going to happen. That's it. Yay. You're tired of listening to me talk. But I'll see you again tomorrow, I'm sure. Or today. What time is it? I don't know. I'll see you.